Morning, everyone. So today we're going to be starting into our third chapter in Chemistry 12. This chapter here will rehash some of the concepts of equilibrium we saw in the last chapter and apply it specifically to what's referred to as solubility equilibrium. We can make solutions, you can bubble gas into liquid, but we're going to primarily deal with dropping solids into liquids. Some of the things will be aqueous, it's going to be dissolved, fully soluble. Some of them will be low soluble and they'll end up as precipitates. So we'll just sort of rehash some of those key ideas from what we introduced in Chem 11 and also integrate a little bit of the equilibrium concepts. So let's just start off here. This one here is going to be Unit 3. This one here is going to be on solubility equilibrium. So this first lesson here, I'm just going to rehash with you some of the key terms that we have seen from before. We are pretty much focusing on this concept of what does it mean for something to be soluble, or the solubility. Solubility describes a chemical's ability to dissolve. Things that are soluble, we can refer to them as, they're going to dissolve. So when you drop them, we're going to assume that in water, because these ones here are soluble, means it dissolves very well. We're going to typically put the aqueous. Aqueous means dissolved in water. Basically, if it's an ionic compound, the dissociation has happened, so the ions are now completely separate. Or if something is told as either low or insoluble, these ones here is dissolves very poorly. So if these chemicals here, they realize they don't dissolve very well, typically we're going to put a solid there. Now, truth be told, everything will dissolve to a certain extent. We just need to set an arbitrary limit. Okay, when do we say, oh, so little has dissolved, basically nothing is dissolved. We'll pull up the solubility chart a little bit more in tomorrow's lesson, but basically they've qualified this word here, soluble, the arbitrary limit that they put in deciding whether it's aqueous or solid. They put it as soluble if you manage to dissolve greater than 0.1 mole per liter. So I'm going to get a solution of 0.1 molar, and it's also specified at a particular temperature. Pretty much for all our tables are at 25 degrees unless otherwise specified. So although everything will dissolve, if it dissolves anything less than this 0.1, if it dissolves 0.09, sure, you may get the smidgen of it actually dissolving in, but maybe so little of it dissolves that when you try tossing in anymore, it just solidifies out right away. So this one here, again, you can think of, okay, I'm dropping in 0.10 moles, right, for every given liter, right? I know I don't necessarily have to have a liter. Eventually, you're going to make a 0.1 molar solution of this, and that's referred to as a concentration. So I'll just rehash with you that concept here. Concentration in solution refers to the amount of dissolved ion. It refers to the amount of solute. So amount of solute. The solute is usually the thing that's in lesser quantity divided by some volume of solution. So to be really technical here, the chemicals themselves will actually take up a little bit of volume, a little bit of size, a little bit of shape, but we're going to imagine that when you drop in the solid here into liquid, basically the liquid, the particles slip and slide past each other. These particles that I'm dropping in will end up filling in the gaps between the liquid particles. So we're just going to say the solution, which is made out of solute into solvent. We're going to always assume that the solvent is water unless otherwise told. So the liquidy background is water. The solvent is the thing that's in greater quantity. We're going to imagine that when you drop in this powder here, it doesn't actually increase the volume of the solvent. It'll still be, let's say in this picture here, 1 liter. We can express concentration and therefore solubility later on. We can express it in grams per liter. So a very common unit because, well, if I have some table salt here and I want to measure out, 5 milligrams of table salt and dissolve it, I'm just going to figure out how many grams have I dropped in per liter. There will be a constant push towards, if I have something in grams per liter, trying to give it instead to moles per liter. The reason why we like moles per liter is because moles will then follow the mole ratio. As we start doing the balance equations again, we can do more predictions that way. So just for example here, let's say we've started off with a container. This container here, let's say it's 500 milliliters, and what I do here is I toss in, let's toss in 2.0 grams of NaCl, right? So in terms of solubility, right, I want to figure out, okay, is this going to dissolve well? I know table salt here, it's a soluble salt, so I would expect that it dissolves. Totally okay that the salt here On the chart here, it will be referred to as soluble. In fact, anything that's an alkali ion will be soluble. But it's not a problem to have NaCl solid out here. Well, I thought we said soluble is supposed to be aqueous. It's only going to be aqueous when you drop it in water. So when you drop this in water here, you would have dissolved the 2 grams into 500 milliliters to express the solubility, to express how much have you dissolved in this container here. I've dissolved 2 grams worth divided by 500 milliliters. Because we were going to eventually have the volume in liters, I'm going to just convert that right away to liters. So 0.500 liters. We can just crunch that math through here. So we have 2 divided by 0.5 gives me 4. Make sure you watch your sig figs here. So therefore, the concentration is 4 grams per liter at present. Okay. So this is not necessarily the solubility, because solubility is not just how much you dissolve. This is so far just a concentration. Solubility also implies the fact solubility is actually referring to the maximum amount that can dissolve. Per volume. So in Chem 11, you had this notion here. Well, you drop in a little bit, it dissolves, no problem. You drop in a little bit more, it dissolves, no problem. You keep dropping in and keep dropping in until the first instant when you drop in. This thing here is very, very soluble. So you drop it in. When you drop in that powder, you start realizing, oh, the powder actually doesn't dissolve anymore. At that point, you've hit the maximum. We're going to refer to that as also saturation as well. That's actually what this solubility tells you. So far, actually, at this point here, if I just dropped in 2 grams and if it's fully dissolved, this right here is just a concentration until I tell you, oh, I actually realize by the time I start adding in 2 grams, some of it starts solidifying back out. So make sure you note here, this is so far just a concentration. You've been able to dissolve 4 grams for a given liter. If this also is the maximum amount that you end up dissolving in, then it's referred to as a solubility. Again, later on, we're going to be doing mole ratio with this one here. So if this really is the maximum amount, 4 grams per liter, have I actually added in 4? No, I've only added in 2 grams. But when I do the ratio in 0.5 liters, it's like having 4 grams per liter. So let's be under the assumption here that you've done this process here. I figured out you can only drop in 2 grams for 500 milliliters. And you've hit this saturation point. How can I re-express this one here in moles per liter? So let's just think about doing a unit conversion here. If you had the solubility expressed in moles per liter, that's also given a name here. We're going to give this the name here, molar solubility. Again, solubility has this notion how much maximum is able to dissolve, but it's expressed in molar. So in this case, as we have it, we have 4 grams for any given liter. I want to get rid of the grams and go to moles. So grams needs to go on bottom, moles goes on top. We're going to actually need the molar mass from our periodic table. So if you just pull out your periodic table here, we're going to have sodium, which is a mass of 23, add chlorine at 35.5. So the molar mass here is the grams per mole, 58.5 grams for 1 mole. 4 divided by 58.5 gives 0.068, and that's going to be moles per liter. So you can say in words, so 0.068 moles of NaCl dissolved per 1 liter of solution. And if I then ask you, well, what's the concentration of the NaCl, you can also refer to this one here. So the concentration, how much have you managed to actually dissolve into liquid? The concentration is the same number, 0.068 molar. So sometimes they do describe, well, solubility, sure, it has this notion. It's the maximum amount you managed to dissolve before this precipitate started forming. Sometimes they say the solubility is actually the concentration of the salt in solution. That's because when you dissolve 0.068 per liter, the concentration is identically 0.068. Again, don't forget about this fact here. Solubility refers to this maximum limit. In fact, in Chem 12, what we're going to do, we're going to, same story, we're going to keep tossing it in here until the precipitate forms. We're not just going to wait until the instant, oh, the precipitate is starting to sit around. It doesn't look like it's dissolving anymore. Macroscopically, it's constant. We're actually going to wait enough that there's actually going to be an equilibrium set up between these two here. So when I hit the solubility limit, when I dropped in the maximum that's going to dissolve, I'm just going to rehash to you here, we have made what's referred to as a saturated solution. That word saturated just refers to it's completely packed full. A saturated solution here contains the maximum amount of dissolved solute, right? Basically, there was only so much liquid here, you could only dissolve so much, and you've actually hit that limit. So that again is referred to as a solubility. That describes how well the solid dissolves. And what we're going to do, we're going to, in Chem 12, we're going to push the limit a little bit here so that solid is actually formed. We're actually going to wait a little while for an equilibrium to be established. So we'll make this note here. Definitely you have to have some undissolved material present. So that means that's the undissolved, that's the precipitate as we would call it. So precipitate is a solid that crashes out of solution here. So some undissolved material present, but here's the key note, in equilibrium with the ions, right? So imagine this, we had our container, we, in this situation here, started off with NaCl. NaCl, I already mentioned, was soluble. So basically, you're able to toss in a ton, it breaks up. You toss in a ton, it breaks up. You toss in a ton, it breaks up. Eventually, though, you're going to hit a point where you've tossed in so much NaCl, when you hit this solubility, you've hit the maximum amount that's going to dissolve, you've now saturated the solution. Now, like we mentioned, the NaCl is just going to sit on the bottom. Macroscopically, it looks like the NaCl doesn't dissolve anymore. But I thought you said it was soluble. Well, remember, there's only so much liquid that can actually handle dissolving the liquidy material here. There's actually an equilibrium set up. What is the equilibrium? Well, one reaction is definitely going to be the NaCl is supposed to be dissolving. So I'm going to write, we're going to see later on in this chapter here, we always put the solid on the left side. NaCl, as it dissolves, this one here is going to dissociate. It's an ionic compound. These ones here are the dissolved ions, the Na plus and Cl minus. Pretty much water comes in and separates the Cl. In that case, the forward reaction, we're going to call it the rate of dissolving. So the rate of this breaking up, now that the ions are so much, it's packed full, you can't handle dissolving anymore, those ions are going to steadily collide as well, and they're actually going to collide together, the Na plus and Cl minus, and they're actually going to reform NaCl, and that's actually going to be the reverse reaction. Because we are going to be in equilibrium, the forward rate has to equal to the reverse rate. This is rate of, you could call it rate of just crystallizing, right? So this becoming a crystal, but because this happens in cycles again and again, we're going to have this notion of recrystallizing. So solubility, when things are saturated, you actually have an equilibrium set up. Macroscopically, it looks like nothing's changing. So I'll make that note here. Macroscopically, macroscopic properties are constant in time. Right? Outwardly, it looks like nothing's changing, and yet if you tag any of these particles here, any of the actual NaCls, you will steadily see them, yep, NaCl does break up, but the reason why macroscopic can stay the same is because the reverse reaction has matched up with it. So just make a note to yourself here, microscopic reactions. So the particles themselves, they're still colliding. Microscopic reactions continue. We have another example of dynamic equilibrium, right? So solubility is this maximum amount. How much can you dissolve per this volume at this temperature? If I compare this to a low soluble salt, let's take silver chloride instead. So no problem out here. We can have AgCl solid, right? It's low soluble. Everything dissolves to some extent. So if you just add a smidgen of this AgCl here, it might be able to dissolve, but being classified as low soluble, basically the bonds are strong enough that water has trouble dissociating this one here. It's not going to take much more beyond that, and this one here would also precipitate out. This one would also end up hitting an equilibrium with Ag ions and Cl ions. So the difference between low soluble and soluble is just how much until it hits saturation. If things are soluble, we're going to need a ton of it before you hit saturation, before you end up hitting this equilibrium, right? So that's just clarifying some wording there. There's two sort of primary types of compounds we can be dissolving. I wanted to specify them for you here. First type of compound we can dissolve, like NaCl, like AgCl, are ionic compounds. Ionic compounds here, these ones here are typically referred to as electrolytes. Basically, they dissolve to form conducting solutions. So let's write down here. They dissolve to form, that's why there's that electrolyte as the terminology here, dissolve to form conducting solutions. It will carry a current, and in general, what do you need for conduction? You need to have charges, and you also need to make sure that the charges are mobile. In fact, the more charges that you have, the more mobility that they have, the more conductive your solution is going to be. So let's just look in a little more detail here. Let's focus in on this NaCl as a solid, right? Even though this one here is described as a soluble salt, Outside of water, before dropping it in, it can be NaCl solid. It's just table salt, no problem. We know it's an ionic compound. We know this forms this regular repeating lattice structure. The lattice is this sort of positive-negative arrangement. When you drop it in water, water is going to basically separate out the positives from the negatives. So what's going to happen is it's going to just show off the Na plus and the Cl minus. We can refer to this reaction here as a dissociation. Dissociation basically refers to our ionic compound has been broken up, so it breaks up. You can also refer to this here as an ionization. These things here start becoming ions. Notice that in the picture, those charges actually already were there. They have Na plus, Cl minus. The electron transfer has occurred. It's just that now that water has come and separated the positive from the negative, now these ions are completely separate, and now they show off their charges. So in this ionization here, it basically shows the charges. Now, just a little bit of background here. In general, charges are unstable. How come water has no trouble breaking up ionic compounds, generally speaking? Water is a polar molecule, so we have water. Even though water overall is a neutral molecule, you may remember from grade 11, oxygen is actually more electronegative. Oxygen is more of a bully, tug-of-warring electrons than hydrogen. So what ends up happening is the oxygen, even though it's supposed to be sharing electrons with these hydrogens, the oxygens hog the electrons to themselves. The oxygen side of the molecule is kind of negative. The hydrogen side is kind of positive. We've actually created what's referred to as a dipole. Even though overall you have no net charge here, because there's a negative side, it notices that there's Na+, water is going to come around and actually surround this Na+. Water, as a neutral molecule, cannot get rid of the fact that there's an Na+ charge, but pointing the negative end here will help to stabilize the positive ion. In a very similar fashion here, we may have our chloride. Our chloride has a negative charge. Which side is water going to point to try to stabilize the chloride? Well, because that's negative, it's opposites that attract, so we end up having the H side that's ending up going to stabilize. We refer to these ones here as complex ions once water surrounds it. This also explains why chloride doesn't need to become, oh, it's chlorine by itself, so it's diatomic. In this case here, it's actually being stabilized by water. Right? We can refer to these ones here as aqueous because they're dissolved in water, aqueous and aqueous. In this case here, as a solid, it is not electrically conducting. So let's check our properties here. Do we have charges? Yes, those charges are already there, but we don't have the mobility. Basically, you have the charges. Charges are just vibrating, right? So basically, the positives and negatives are just vibrating in place. They don't have a lot of kinetic energy because they can't move from one side to the other side, not conductive. Upon dropping them in water, suddenly those same charges, they're now sort of released, and now in the aqueous state, sure, they're actually surrounded by this water here, they're actually free to roam around. Because charges can actually move, they are actually electrically conducting in solution. Electrically conducting. And in fact, the higher the molarity, the higher the concentration of Na+, there's more charges that can carry the current, the more conductive it's going to be. One other caution here, so most ionic compounds here, especially if they're soluble, they're called electrolytes, they're electrically conducting in solution. What if I had a larger compound, let's say ammonium sulfate? What happens to this guy when it dissolves in water? We're going to see on our solubility chart tomorrow as well. Well, ammonium salts are also fully soluble. So this one here is going to fully break up. Just be careful of this ammonium here. It's actually covalently bonded inside of it. Water is not good enough to actually break apart the covalent bonds. All water is going to do is separate the ammonium groupings from the SO4 grouping. These are polyatomics. And basically, water just separates positive from negative. It breaks up the lattice here. So just be careful when you show these dissociations. Make sure you keep the polyatomics together. Ammonium and we have sulfate. Well, we have a 1:2 ratio, so I still need that 2 there. Same thing, we get ions in solution, so definitely conductive. Let's compare that to the other situation here. First grouping here are ionic compounds. What if we toss in covalent compounds? So covalent compounds, not just like polyatomics here that end up having charge anyways, but just in literal covalent compounds. We usually refer to these covalent compounds as individual molecules. So they're actually going to form what are referred to as molecular solutions. And these ones here are not conductive. Form molecular solutions that do not conduct. So that's the first sort of easy question. They're going to give you, here's a random compound here. Is it going to be an electrolyte or not? You're basically looking. If it's an ionic compound, probably conductive. If it's a covalent compound, probably non-conductive. So an example of this here, let's start off with water. Let's take methane as our molecule. So methane is CH4. It's a non-metal. Hydrogen is using its non-metal properties here. CH4 here by itself is just an individual molecule. No lattice, no repeating pattern, anything like that. So no charges ready. You can dissolve methane into water. You can manage to get CH4 here swimming around the liquid. But just like I said before, the covalent bonds here, dollar for dollar, are stronger than an ionic bond. Water can't actually separate the C from the H, so therefore the C and CH4 stays intact. When we check our two properties, do we have charges? Well, no, we don't have charges, although we do have the mobility. I need both features to be conductive. Because I don't have the charges, there's no current that's carried. Okay, so just keep that in the back of your mind. You need to have charges. You need to make sure that they're mobile to make sure that this is conductive. Right? So let's just work through another quick example, and then we'll finish off just calculating through a dilution mixing style question. Right? So I'm going to give you this example here. 1.5 grams of magnesium hydroxide can dissolve into 250 milliliters. Notice, even though I'm going to always do per liter later on, your actual solution sitting in front of you could be actually less than that. So 250 milliliters to form a saturated solution. That's our word. So a saturated solution. I want you to calculate the concentration of magnesium and the concentration of hydroxide at equilibrium. Okay. So let me just start off with a quick picture of what we're doing here. We start off with a container. We have about a cup. So 250 milliliters, you can assume that that's water. We find that we can drop in 1.5 grams. So the solid that we're dropping in, 1.5 grams is magnesium hydroxide, MgOH2. You manage to drop this in here, right? Let's say I only drop in, let's say 1 gram. Oh, I find more dissolves. You keep dropping. By the time I drop in 1.5, this is the perfect limit that you've actually end up hitting saturation. Remember, saturation implies we're in equilibrium. For equilibrium, we need both reactants and products present. So therefore, once I drop in 1.5, I hit that maximum limit. So that's actually referred to as solubility. I now have that undissolved material present, and now I'm just going to wait long enough for the solid to start dissolving and the dissolved ions to be matched up in the recrystallizing rate. So this is referred to as a solubility. Again, let me just clarify for you here. Solubility, this number, remember, it's the maximum solute that can dissolve. It's not just a concentration. It's not just how much has currently been dissolved. We're told that this is exactly the minimum amount that you need to form saturation. This is basically the maximum amount that your liquid can actually dissolve in. So far, just like we did in the earlier question, we have 1.5 grams. I managed to dissolve in 250. I'm going to express it per liter, so let's make that 0.25 liters. Whenever you do that conversion, make sure you keep track of your sig figs. So this one here, I made it 2 sig figs here, so that's just going to be 2 sig figs. That already is a solubility in grams per liter, but because later on we're going to need to do the ions, I need to again change this to moles per liter. So they might first ask you to calculate the molar solubility. Again, going to your trusty periodic table here, magnesium is 24.3 plus twice, oxygen is 16 plus the 1. So we get 58.3, coincidentally very similar to the molar mass from earlier, but you just add it up for the salt that you're given. 1.5 divide 0.25 divide 58.3. The molar solubility this time is 0.10, right? So that's just the name of it. So if they say calculate molar solubility, it's basically this solubility number, but expressed in moles per liter. This is the concentration upon dissolving 0.10 moles for a given liter. Remember, I don't actually exactly have a liter, but by ratio, it's like 0.10. Because we have this molar solubility here, we're ready to do the dissociation. So take MgOH2. MgOH2 is going to break up to form Mg ions and 2 hydroxide ions. This is sort of the easier way of doing it here. We've made a saturation solution by dissolving a solid. I'm going to make that note right now, and then we're going to come back to it in the upcoming lessons. I managed to dissolve 0.10 molar. So 0.10 moles of solid dissolve per liter. So that's why the concentration is 0.10. Well, because I have this thing here expressed now in moles, we're going to now follow the mole ratio. So if this is a 1-to-1 ratio, when this breaks up, your concentration is going to be 0.10 of the magnesium, 1-to-2 ratio for the hydroxide, we're going to get 0.20 molar. When you dissolve a solid, your ions will follow the mole ratio. Ions follow the mole ratio. It is sort of implied here. Yes, while we have some solid present here, solids have a constant composition. We never really talk about concentration of a solid. We just have some powder sitting there. It's implied that any little bit of solid that's actually broken off, it actually had to dissolve into solution and end up forming 0.10, 0.20. So this is effectively gone, or sort of the particles that actually went to break off, becoming 0.1, 0.20, those particles are gone, and yet in a saturated solution, we still have some solid left over. Now here's the strange thing here. If this is the maximum limit, let's say I drop in a little bit more magnesium hydroxide. I can drop in more solid, no problem, right? MgOH2, MgOH2, right? I'm going to drop in more chunks of solid, but because I've hit the saturation limit, no more ions will actually dissolve into the mixture. So you might have more or less any extra MgOH2, we'll just say here, remains undissolved. It just sits around extra. I have a lot more solid present, so let's make that note here. We may have more solid, but when we say the concentration of solid, we did this a little bit when we did our KEQ from the last chapter here. Solids are always ignored, but the concentration of solid is constant. They have constant composition. I always think of a concentration of solid as like a density thing. You may have more powder, sure. You have more powder, but it's also taking up more room. That ratio ends up not changing. So later on, we start talking about Le Chatelier again. As I add magnesium hydroxide, you might actually have more powder, but it's just going to sit around there. It's not going to be able to shift this equilibrium. In fact, if you tag these particles here, the particles themselves might constantly be dissolving. Other particles are constantly recrystallizing. Macroscopically, it looks like that pile is just sitting there. This is the first way of making a saturated solution. I'm going to just hint at one other way of doing it. We've actually seen this other way back in grade 11 here. This way here is referred to as a sort of dilution mixing style problem. So let's say I intend to make the same container. I want to make a saturated solution of magnesium hydroxide. Well, in the first case, I started off with the solid, it followed the mole ratio, everything was nice. Well, all I actually need is I need to put in magnesium, I need to put in hydroxide, I basically need to max out how much manages to dissolve. These ones will then crystallize out and they will end up forming our solid. So let's just finish up with this question here. I'm just going to put some random numbers to this here. Maybe I'm at a different temperature. Let's say I add 10 milliliters of magnesium nitrate. I'm going to add that to 20 milliliters. Just to color code these solutions here. 20 milliliters of, let's make it sodium hydroxide. Again, at first you might be like, whoa, what happened to where did the nitrate come from? Where did the sodium come from? It turns out, yeah, while I may only be caring about the magnesium ion, I may only care about the hydroxide in this particular problem, you're never going to have a pure bottle of magnesium ion or hydroxide ion. Charges in general are unstable. They always have some counterbalancing ion. What I've done is I've chosen a soluble salt. When this guy here breaks up, this guy ends up breaking up to form Mg ions and 2 nitrate ions. This NaOH will break up to become Na+, one thing positive, one thing negative. Basically, I'm focusing, well, there's the magnesium I need, and there's the hydroxide I end up needing. Now, one extra thing here we started seeing in Chem 11, when I mix in 10 mils and 20 mils, you notice the total pool size is now 30 milliliters. Now, some solutions, when they mix into each other, it's actually the liquid particles are going to slip and slide into the gaps left behind by other particles. So sometimes this may not be exactly 30, but just for simplicity, we'll just say 10 into 20 makes 30. What's happened first is, although I may know the concentration, let me give you the concentration. Let's say the concentration here is 0.50 molar MgNO3, and let's say it's 0.80 molar, totally making up those numbers there. So let's say those are the starting concentrations, but that was only when I was in 10, when I was in 20. But now that I'm mixed into a total pool size that's larger, basically the number of swimmers here are now going to swim in a bigger pool. The magnesium nitrate gets diluted, and the NaOH also gets diluted. So if you remember for a dilution formula here, we do a C1V1 equals C2V2. Basically, it counts the number of particles, and it says, well, the number of swimmers are still going to be there. We're going to need to do a dilution calculation for the magnesium nitrate, as well as one more for the sodium hydroxide. C1V1 equals C2V2. Most common problem I see in this section here is people do, oh great, I have a C1, I have a V1, and then they go C2 and a V2. Remember, these are totally different chemicals, right? I shouldn't compare these chemicals with each other. In fact, in this case here, it's actually the V2. V2 should be the total volume. Both of them, when you mix them 10 into 20, both of them start swimming into 30. So let's just set up a ratio here. We're just going to use 10 in milliliters. This formula here will work as long as your units are consistent. 0.50 molar is the MgNO3. What's the new concentration if my new volume is now actually 30? And in a similar fashion on the other side here, I started off here at a concentration of 0.80 molar. My volume was 20 milliliters. What's my new diluted concentration when my final volume again is 30? Both of them have been diluted down. That's what a mixing question is. So we're going to multiply this 10 times 0.5 divided by 30. My concentration, my new magnesium nitrate concentration here is actually going to be 0.16. Let's just do 0.17 for 2 sig figs. Notice that this concentration has dropped. No surprise there. It's like diluting apple juice here. It's going to taste less strong. If I do the other side here, 0.8 was a little bit bigger. I have more volume of it, times 20 divided by 30. The concentration on this one remains 0.53. And this one here is also lower than what it started. This one here is so far concentration of NaOH. Now, let's say by the time you add this, again, there's this notion of when I just mix this together, I just start seeing a precipitate forming. It's totally possible that maybe the concentrations are so low, maybe the ions are perfectly fine dissolved. Mg ions, hydroxide ions, we're going to actually use our KEQ as actually a test of whether the ions are enough. Let's say I've worded this in such a way, when you mix these exact amounts, let's add this terminology here. Let's say a precipitate, let's say PPT, a precipitate just forms. So we've just hit this saturation point. We've just hit this limit where the maximum is dissolved in. You'll notice first thing is magnesium came from one solution. Magnesium is a 1-to-1 ratio with the magnesium nitrate. So this one here is actually the concentration of magnesium. Magnesium that I managed to put in is 0.17 upon dilution. The hydroxide that I managed to put in here, the sodium hydroxide was 0.53. Again, it's a 1-to-1 ratio with hydroxide. The hydroxide amount is actually going to be 0.53, just 1-to-1 ratio. And if they now add this statement here, this is the sort of that perfect point when I just hit saturation. Basically, when the magnesium hits this number and the hydroxide hits this number, I'm now fully saturated. Usually what I do is if you identify for me what the solid potentially is, the only solid in this case here is the magnesium hydroxide I was looking at. We're going to always put the solid on the left side, even though, wait, the solid here is actually a product. When the magnesium ion actually runs into hydroxide, we still want the solid on the left side. More on this in a later lesson here. This is going to dissociate to become magnesium ions and 2 hydroxide ions. And so far what I've told you is the magnesium ion is currently 0.17. What's the hydroxide concentration? I already found my hydroxide concentration is 0.53. Don't worry about this too, because mole ratio would only matter if I had started off with the solid. I didn't start off with the solid powder. The magnesium came from one solution. The hydroxide is exactly 0.53. And now we have these two amounts. Hey, wait, these two actually don't follow the mole ratio. Well, they don't have to, because magnesium came from its own solution. It can have its own concentration. This one can have its own concentration. They're not actually stuck to this 1-to-2 ratio. So here's the second way of making a saturated solution. This is mixing solutions together. I just rehashed with you a little bit of dilution calculation, C1, V1, C2, V2. And you'll notice here in this case, your concentrations don't follow the mole ratio. So just keep in mind there's these two main ways. Sometimes they follow the mole ratio, sometimes they don't. Whenever you mix two solutions, they won't. Right? So I'll leave it off there, and we'll pick it up from there tomorrow. Thanks, guys.